So this is a formula that usually people learn when they're doing like radiative heat transfer. But if you have a hot object, this is the rate at which it transfers energy to its surroundings via blackbody radiation. Okay, and sometimes there's like a little thing out in front here, the emissivity of it. But for a star, we're just going to assume that that's 1. Okay, this is a constant. This is our Stefan Boltzmann constant, 5.67 times 10 to the minus 8th. Okay, and A is the area, the radiative area that a star has, right? So stars that are big can put out a lot of light because they have a lot of radiative area. And then obviously stars that are hot put out a lot of light. And notice that that's to the 4th power. So if you double the temperature of a star, God, let's see, that's 16 times the power output. Is that right? 2 times 2 times 2 times 2. That's 16 times, right? Okay. So hot stars put out a lot of light because they're hot, right? And then big stars can also put out a lot of light. And of course, if you're big and hot, then you put out a lot of light. Okay, so let's see. Notice it's got to be kelvins. Remember that the area of a sphere is 4 pi r squared, and we're ready to go to our example. Okay, so the sun has a surface temperature of, hey, that's the sun. Look at that, right? And a radius of about that. So what's its luminosity? And basically, the idea of luminosity is what's the power output? If you replace the sun with a light bulb, and you went to the store to buy it, what wattage would you use, right? So I think our formula was L is Stefan Boltzmann constant area temperature to the 4th. Pretty simple thing, right? So this is going to be equals 5.67 times 10 to the minus 8th. And that's watts per meter squared, and then what is this? It's got to also be like Kelvin to the 4th, doesn't it? There's got to be the units. I'm just looking, I'm trying to fudge them here. Okay. And then we're going to multiply that by 4 pi, and then our radius is 6.96 meters, and that's going to be squared. Right, and then that's going to cancel our meters squared, right? And then our temperature is 5787 kelvins. That's to the 4th. Okay, so let's see, 5.67 E minus 8 times 4 times pi times 5787. Oops, wrong number. Okay, let's see, 6.96. 6.96 e to the 8th, and that's squared, right? Times 5787 times 10 to the 4th. Nope, not 10 times to the 4th. Raised to the 4th power. Raised to the 4th. Okay, there we go. Do I have it all? It looks like I do. Let's hit enter and see what I get. Ooh, I got the same answer, right? Notice our units, Kelvin to the 4th, Kelvin to the 4th goes away, meters squared cancels that, and you just get watts, right? The answer I'm getting is 3.871019, blah, 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 right? Times 10 to the 26th watts, right? Okay, and then I guess what we have 3 sig figs because of this guy. So you'd have to say this. I'm going to do another example. It's not on your sheet. Don't feel obliged to do it. But if you want another example, keep watching. And if you don't, go to the next video. Okay, so let's see. A star has a radius. We got the radius. And we've got its luminosity, right? So we want to know the temperature. So let's see. L is sigma times area times t to the 4th, right? So L divided by sigma times the area. And I guess we have to raise that to the 1/4 power. Is temperature. Golly, look how smart I am. Okay, so 4.2 times 10 to the 26th watts divided by 5.67 watts per meter squared Kelvin to the 4th. All right, and then we've got, that's part of the denominator, and then we've got to put the area there. Bigger denominator. Okay, let's see. 4 times pi times 5.0 times 10 to the 8th. I just love parentheses. They just make everything so tidy. Okay, so let's see. Da-li-da. Oh, and then we got, oh my god, we got to raise that to the 4th power. Sweet mother. What are we going to do? Okay. Okay, so let's look at our units here. Watts. Say, hey, watt, hit me. Okay, meters squared, and that's on the top of the denominator, and that's on the bottom of the denominator. And then you have 1 over kelvins to the 4th, to the 1/4, and that'll be kelvins. Okay, so 4.2 e to the 26. Oh, I got to put this all in parentheses, don't I? Parenthesis 4.2 e to the 26th divided by beginning of the denominator 5.67 e times 4 times pi times 5e8 squared. Right parenthesis end of the denominator, right parenthesis end of the expression raised to the parenthesis 1 divided by 4, right parenthesis. Wow, it's complicated. Let's see what I get. And I get 6968.33 kelvins. We have only 2 sig figs. So if we round it to there, we've got to round it up, right? So 7.0, which is why that's how I wrote it there. Yeah. That's not too hard, is it?